Okay, I'm going to get started. I wanted to move on today from the work we've done on electricity and the work we've done on magnetism to a phenomenon that's called induction and to the world of electromagnetism. So we spent about 9 lectures on electricity. We kind of lingered there. I'm going to refer to that now as electrostatics, and it was about charges, stationary charges. We spent a few lectures on magnetism. We kind of rushed through that. I'm going to refer to that as magnetostatics. It involves steady currents. What we're moving on to is away from this sort of frozen landscape of stationary electrical charges and frozen landscape of steady currents in magnetism. We're going to move on to things that change in time, things that vary in time. And that's the world of induction, and that's the world of electromagnetism. And so that's what we're beginning now. Specifically, in today's class, I want to talk about these topics. So the first topic is a discovery, and it's the discovery of induction, which is the discovery of what we call induced currents and what we call induced voltages due to a change. The change is a changing magnetic field, a changing magnetic flux. So that's the first quantity, the first item. I want to then go on to a law that describes this effect or phenomenon of induction. I want to talk about the magnetic flux law. To talk about the law that describes induction, I've got to introduce the concept idea of magnetic flux. So the second 2 bullets are introducing magnetic flux and then introducing the flux law. So that's the route through today's class. We'll do a bunch of examples on the way, a bunch of illustrations on the way. This is a point I wanted to make. When we talked about electricity, we talked about it as kind of a separate force, a separate world of electricity, electrostatics I'm now calling it. When we talked about magnetism, we talked about it as kind of a separate world, a separate landscape of magnetism. I'm calling it magnetostatics now. But actually, and it's pretty obvious, they're not just 2 separate worlds, because at the heart or at the roots of electricity and at the heart or the roots of magnetism is electrical charge. It's an electrical charge that causes electrical forces between electrically charged objects, and it's moving electrical charge, electrical current, that causes magnetic forces between charges. So at the roots of electricity and at the roots of magnetism is something that's common, charge, and so really they must be inseparable. They're both due to the same basic quantity of nature. In exploring induction, what we're doing is exploring more connections between electricity and magnetism, more relations between electricity and magnetism. And we'll see that there is much more connection than just the fact that their electric forces, magnetic forces are due to electric charge. So that's the goal. Okay, I want you to go back to this picture. I think I showed this picture earlier on in the semester. But it is an insightful picture. It's the picture that shows these fluorescent lamps arranged vertically. These fluorescent lamps are lit, but these fluorescent lamps aren't connected directly to any wires, any supply of electricity, any power supply. Rather, they're lit because they are literally bathed in electric and magnetic fields that are created by the overhead power lines. And they're bathed in those electric and magnetic fields, and those electric and magnetic fields through induction, this new phenomenon, induction, is lighting those lamps. And so this is a classic example of electromagnetic induction, producing induced currents that we're going to talk about, induced voltages we're going to talk about, and lighting the lamps. Okay, got lost severely. Okay, I want to introduce two people, two scientists that were kind of the grandfathers of induction and joining together of electricity and magnetism. One of them, we talked about him before, Michael Faraday, famous English scientist. He's very famous for actually having no training whatsoever. He didn't go to school, basically. But he had this fantastic intuition. He had this intuition that led us to the idea of fields as carriers of forces. He had this intuition about induction, and he came up with experiments that detected induction and came up with a law of induction, all that based on no formal education. So he's really the grandfather of induction. Also want to talk a little bit about this is an American scientist, Joseph Henry. So Faraday published the discovery of induction, or the uncovering induction, just ahead of Henry discovering induction, uncovering induction. However, Henry went on to develop induction, develop a lot of the technology that's associated with induction that makes possible our modern lives. Our modern lives are based on, a lot of it's based on induction, electromagnetic induction, because that's how we get power out of the power sockets, is based on electromagnetic induction, and many, many more things. Our communication technologies are based on electromagnetic induction. So he took the ideas, concepts of induction, and turned them into all our modern technologies. You know, we think of Apple, and we think of Steve Jobs as you know, giving us Apple and iPhones and all this stuff, but really that's all on the shoulders of that communication, that wireless communications, all on the shoulders of Faraday and Henry, who discovered and developed induction, because wireless communication is all based on electromagnetic induction and their discoveries. Okay, so now let's talk about what induction is. I'm going to talk about this little arrangement here. So I've got 3 slides in which you'll keep seeing this arrangement here. And this arrangement here is the arrangement that Faraday used to discover induction. And as I said, Faraday had some interesting intuition. He had this intuition about electric and magnetic fields carrying electric and magnetic forces. He had intuition about there being a connection between electricity and magnetism. And he looked for that connection in this simple setup here. So what does it involve? So his setup involved a magnet. So here's a magnet, a bar magnet with its north pole where the field lines are emerging from, south pole where the field lines are returning to. So it's creating a surrounding magnetic field. So that's a magnetic part of his setup. And then a second part is this, this little electrical circuit here. He's got a loop of wire in black, and he's going to measure the voltage or the EMF across that loop of wire in volts. And so here's just a voltmeter. Obviously it's not his voltmeter, but this is our cartoon voltmeter. And so this is the electric part of his arrangement or his experiment. So he's got a magnetic part with a magnet. He's got an electric part where he's going to measure, with a loop of wire, he's going to measure the voltage. Now, so if you just set this up, and set up this arrangement and just sit it there on a bench, what voltage do you measure? We're bathing our loop of wire in this magnetic field. Well, what voltage you measure is 0 volts. You measure nothing. There's no effect if you just sit the bar magnet on the bench next to the loop of wire and you just watch it. There is no effect. There is no voltage in the wire. However, what Faraday noticed was, let's see, yeah, this one. When he brought the bar magnet up to the loop of wire, so in that moment when he was assembling the experiment, so this is a moment of change, right? The experiment was put away in the cupboard or whatever, and he took it out of the cupboard and he put it together. At that moment, he brought the bar magnet up to the loop of wire. There was a sort of instantaneous or momentary voltage across the loop. And we call that the induced voltage. The current that flows is the induced current, and that effect is induction. The moment you bring, so look at the picture here, I'm moving the magnet close up to the loop of wire. At that very moment, there is an induced current. There is an induced EMF. There is an induced electrical signal, and we can measure it. So the key there was the fact that the magnetic field was changing at that moment. We bring the bar magnet up. There was no magnetic field, and then there is a magnetic field. That creates induction. You know, at the end of the day, when he put his experiment back in his cupboard, then he also noticed an effect. So here he is disassembling his experiment. He's taking the bar magnet away. And he noticed that at that moment when he took the bar magnet away, when the magnetic field went from a magnetic field bathing the loop of wire to not bathing the loop of wire, there was again a signal in the, there was a current, electrical current in the loop of wire. There was an electrical voltage across the terminals of the loop of wire. There was an electrical signal that was produced, again, when the magnet changed, magnetic field changed. So those three slides show you the important effect involved in induction, that if the coil is just sitting there without the magnet around, there's no induced EMF, no induced current. If the coil is just sitting there with the magnet nearby, there is also no induced EMF, no induced current. But when there's a change, when you bring the magnet up or take the magnet away, when you increase the magnetic field or decrease the magnetic field, at those very moments, those very instants, there is an induced current and it is an induced EMF, and that is induction. Let me demonstrate it. So I'm going to put it on the camera, if I can do that. So here we are. Maybe I'll try and make it a bit bigger. Okay, what you see on the camera is these two experiments. These are actually two experiments that Faraday did. The one on your right is the one I described with the bar magnet and with the loop of wire. And the one on the left here is where he has two coils of wire instead of a bar magnet and one coil of wire. So I'm going to go through both of these. So here's the bar magnet, and here's the loop of wire. So this loop of wire is not just actually one loop of wire. You get a bigger effect if instead of one loop of wire, you have many loops of wire. So each loop of wire adds to the induced current, adds to the induced EMF to make a bigger induced current, a bigger induced EMF. So we're going to see that. Now, I've got the bar magnet. If you read this, is just like one of the bar magnets I've shown you before. There's a north pole and a south pole. The red end is the north pole and the white end is the south pole. And so I'm going to put that into and out of the coil. And you're going to watch on this voltmeter the induced EMF, the induced voltage. And so we're going to be able to see that. You notice right now, if you look on the screen, or if you look here, you know, the magnet's not very near the coil, and there's no induced EMF, no induced current. The needle is standing vertical. But if I bring the magnet up, you see a deflection. So it deflected to the left. Now I've left it inside the coil. It's not deflected now. But if I take away, it deflects to the right. That's induction. So again, the magnet's in the cupboard now. There's no induced current. I bring the magnet up. I get a momentary induced current. The needle deflected to the left. I put the experiment away in the cupboard, and there's a deflection towards the right. And so that's induction. And that's the basis of all our modern wireless communication. That is communication wirelessly. The magnet is talking to the coil wirelessly. There's no physical connection. It's just through the surrounding space, empty space. Let me show you this one. This was the other experiment that Faraday did. So it too has a coil of wire that's connected to a voltmeter to measure the induced current or measure the induced EMF. So that's this arrangement here. We got the coil of wire, and we got the voltmeter again, and you see the needle is standing vertically. There's no induced current, no induced EMF right now. But instead of bringing up a second magnet, a magnet close by and taking it away, what we've actually got is a second coil. Now this is a solenoid. You know this produces a magnetic field, and we're going to place this coil inside the larger solenoid, which can produce a magnetic field. Now right now the power supply is on, but I got a switch, and that switch is open. So this solenoid is not activated. The magnetic field is not on here. So this is another way that I can switch a magnetic field on and off. In the case on the right, I moved the bar magnet close by and then took it away to switch on and off a magnetic field. In this case, I just need to press the switch to put on the magnetic field in the outer coil, and we'll see what happens on the inner coil. Now, importantly, right, they're not connected to one another. These two circuits are not connected to one another. If they talk to one another, this is wireless communication. Okay, so watch while I'm going to close this switch, and I'm going to hold it shut. So we saw the needle deflect to the left, to the right. But now the circuit's still complete. I'm holding the switch closed. There is a magnetic field here, but there is, you know, while things aren't changing, there's no induced current, no induced EMF. If I open the circuit, suddenly the needle deflects to the other direction, towards the left. So when the magnetic field changed, when it went away in that case, we got an induced current and an induced EMF. And so I'll just do it a couple more times, so much fun. Okay, switch on the circuit, we got a deflection. The magnet's on right now. We're seeing nothing right now because nothing's changing. Turn it off. Get a deflection in the opposite direction. The magnetic field went away, but now it's gone away. There's no induced EMF, and so on and so forth. So I can communicate. Look, I can do Morse code. I can communicate wirelessly. This is literally the beginnings of wireless communication for your iPhone. Okay. I should say that at the time, that experiment, right, that was considered close to lunacy to do that experiment, because at the time, electricity was this separate world, magnetism was this separate world. To look for a connection between electricity and magnetism was a very strange thing to do. That's why kind of Faraday is sort of this inspired person that looked in strange places and discovered strange things. Discovered electric and magnetic fields, and he discovered electromagnetic induction. Okay. Don't think I need to say that. So the next step in Faraday's work was, well, I've uncovered electromagnetic induction. When I switch on and off a magnetic field, I can induce a electrical current, electrical voltage in a circuit. I've discovered that effect. What is the law that describes that fact, that observation? What is nature's law describing electromagnetic induction? So he went searching for a law of nature, an equation, a formula to describe induction. That sounds like a tough thing to do. Sounds like a tough thing to do. This is a law kind of unlike, Coulomb's law for electricity, about the interaction between a pair of charges, or maybe I'll pick Ampere's force law. That's the law we met last class, the force between a pair of currents. The law we've got to look for here has to depend on time, because it's something changing in time that creates the induced current, induced EMF. Coulomb's law is just kind of this static frozen law. It doesn't depend on time. Ampere's force law, the force between two currents, it is a static law. It doesn't depend on time. Now we're looking for something new, something much more modern in a way, laws of physics that depend on, that change with time. So this is a new world. To introduce that law, I'm going to first introduce a concept that's of magnetic flux. Now, I can introduce it pretty quickly because the idea and definition of magnetic flux just resembles the idea, concept, definition of electric flux. So I'm going to base the next few slides on magnetic flux, on what we learned about electric flux. So just to remind you, this is our definition of electrical flux, and it's a quantity that is related to electrical field that carries electrical forces. So in defining electrical flux, we thought about a surface. So that's this rectangle here. And we thought about the field in the neighborhood of the surface. In particular, we thought about the field passing through the surface. And it's in terms of that surface and that field that we define the electrical flux. To quantify it a bit, I would think of the field as described by an electrical field vector, E, and I would think of the surface described by a surface vector. It has some length that's in square meters or square centimeters, describing the size of the surface. It has some orientation, a direction that describes the orientation of the surface. It points perpendicular to the surface. Anyway, to describe the flux, which involves the field and the surface, we introduce a field vector and a surface vector here. And then here was the equation for the flux. We wrote it a couple of ways, because sometimes one way's handy, sometimes the other way's handy. But let me describe this way here. The electrical flux, phi E, is equal to the strength of the electrical field over the surface times the area of the surface, cross-section of the surface, times the cosine of this angle theta, where this angle theta was the relative direction of the two vectors, the electrical field vector and the area vector. So it was the angle between those two vectors. If we wanted to visualize electrical flux, we could visualize electrical flux by thinking of it as kind of a measure of the number of field lines that pass through the surface. If you count up the number of field lines through a surface, that's in proportion to the electrical flux. So more field lines is more flux through the surface. Less field lines, less flux through the surface. All that applies to magnetism. You can also think of, in addition to an electrical flux that's related to the electrical field, you can think of a magnetic flux that's related to the magnetic field. And that's what this slide is. So when I made this slide, saved a bit of time, all I had to do is remember the lecture that the previous slide was in, the electrical field flux, and then just modify it to make the magnetic flux. So in the picture, to think about magnetic flux, so I got to think about a surface. I got to think about a surface bathed in a magnetic field. So I pictured that. I want to think about the magnetic field vector that represents the strength and the direction of the magnetic field. I want to think about the surface, the area vector that represents the size of the surface and the orientation of the surface. And then I can define the magnetic flux, call it phi subscript b now rather than phi subscript e, in terms of the magnetic field and the surface vector. So we can write it this way here as the magnitude of the magnetic field over the surface, its strength, times the area of the surface, the number of square centimeters or square meters of the surface, times this cosine theta factor, which is the cosine of the angle between these two vectors, between the vector b and the vector a. Again, the number of magnetic field lines crossing the surface, if we want to visualize flux, the number of field lines is in proportion to the flux. So more magnetic field lines crossing the surface, that's more flux. Less magnetic field lines crossing the surface, that's less flux. I wanted to stress one important point about magnetic flux. It's the same as a very important point about electric flux. It's easy to understand that the flux through a surface depends on the strength of the field that the surface is immersed in, whether it's an electric or a magnetic flux, electric or a magnetic field. It's easy to understand that the flux will depend on the size of the surface, whether you've got a large surface, square meter, or a small surface, square millimeter. It's going to depend on that size. But it's also important to recognize, understand that the flux depends on the orientation of the surface in the field, the relative direction between the vector B describing the magnetic field orientation and the vector A describing the surface's orientation. And so this is, again, I just look back at the old electrical flux lecture slides, and modified a slide that describes the dependence of the flux on the orientation of the surface in the magnetic field. So in this picture here, in this sketch here, I've got a uniform magnetic field. So everywhere the magnetic field is the same strength. I've got a surface that has the same surface area in the left here, in the center here, and on the right here. The only thing I'm changing in these three pictures of these three surfaces in this magnetic field is the orientation of the surface. That's the only thing that's changed, and that's the only thing that ends up changing the flux. In the picture on the left, I've got the area vector, so that's the bright red vector. It's in the same direction as the magnetic field. So the angle is 0 degrees. That's going to make the largest flux. That's how to collect the largest flux in your surface. In the sketch in the center here, I've reorientated the surface. I've now got the area vector, this bright red vector, pointing perpendicular to the electrical field lines. That's going to make the smallest flux. That's going to make 0 flux because cosine of 90 is 0. And then over here on the far right, I've orientated the same surface somewhere between those two extremes, with A parallel to the magnetic field, A perpendicular to the magnetic field. That makes some intermediate flux that's somewhere between the largest and the smallest, and is determined by the cosine of this angle between the vector A and the vector B. And so this is a reminder that not only does flux depend on the field's strength, not only does the flux depend on the area of the surface, it also importantly, it's especially important for magnetic flux, we'll discover as we look at applications to technology, that the flux depends on the orientation of those two vectors. You can see it by counting field lines through the surfaces. So this surface over here has 1, 2, 3, 4, 5, 6, 7, 8 field lines that pass through that surface. That's going to be a big flux. This surface here actually has no field lines passing through this surface. Look, this one upstairs here glides over the top. This one downstairs here glides below the bottom. They don't cut through this surface. No flux through this surface. And then this one over here on the far right, where we said the flux was somewhere in between the two extremes. Well, let's count the field lines. 1, 2, 3, 4, 5, 6. It is intermediate between the two other surfaces. Okay. One more example of this. Let me show you the demo here. No idea what I'm doing. Quiet. I got to practice this a little bit more. Okay, I've got this globe. And you may recall that the Earth is magnetic. And you may recall that the geographic North Pole is actually the South Pole. And the geographic South Pole is actually the magnetic North Pole. Actually, it's not even quite that. I had said that the geographic South Pole is kind of near the magnetic North Pole, and the geographic North Pole is kind of near the South Pole, the magnetic South Pole. This little flag here, this is indicating the geographic, this is indicating the magnetic South Pole, and it actually is in Greenland. So the geographic South Pole is in Greenland, and the North Pole is way down here, somewhere down here, indicated by this red flag. Now, in the question here, it says, well, look, Greenland's way upstairs, and what's the country way downstairs? Argentina. I randomly picked it. Argentina has a bigger surface area than Greenland, a somewhat bigger surface area than Greenland, and I listed them there. It's about 20% bigger. So if Greenland and Argentina want to compare themselves, Argentinians might say, well, we've got more surface area than Greenland. On the other hand, Greenland has more magnetic flux through Greenland's surface. And this is an example of the importance of the orientation of the magnetic field vector and the area vector in determining the magnetic flux. So the magnetic field where Greenland is and where Argentina is the magnetic field strength is very similar. The surface area of Argentina is bigger than Greenland. So why doesn't Argentina have a bigger flux than Greenland? The reason is that Greenland, this is right where the South Pole is. The magnetic field lines are coming out of the South, heading straight into the South Pole. So that means that the field is perpendicular to the surface. It means that the field and the A vector describing the surface are at 0 degrees. They're pointing in the same direction. I can show you that here. If I get, this is a little compass. If I place it here, You can't really see it. Well, if I place it here maybe, you see that the compass needle is standing vertical. That's because the field is going straight in to Greenland. So that makes a large flux through Greenland. But if we went down to Argentina, my geography is bad, so I don't know where it is. It's somewhere over here. You know, Argentina, well, it is to the south, but it's actually not really very close to the magnetic North Pole. And in Argentina, wherever I'm putting this now, the field lines are actually, if you're in Argentina, the field lines are kind of skimming over your head. I mean, they're coming out of the ground a little bit, but they're mainly parallel to the surface. The angle between the magnetic field vector and the area vector in Argentina is a large angle. So that makes the flux, the magnetic flux, small. Okay. So now we've introduced flux, let's talk about the flux law. Let's talk about Faraday's flux law, Faraday's magnetic flux law, Faraday's magnetic flux law for induction, that describes induction. It's a very interesting equation. It's in a way, it's a very simple equation. In a way, it's a very subtle equation. We'll be talking about it in today's class. We'll be talking about it in next Tuesday's class. We'll be talking about it in next Thursday's class. So we're going to spend a lot of time on what at first sight might seem to be a rather simple equation. Here it is. This is Faraday's flux law. And so we're going to start working on it today, and we'll continue working on it and its consequences and its ramifications for technology and our lives over the next 3 classes. Okay. So let me return to, I'm going to return to 2 slides. There was this slide here where we introduced the effect of induction, where I brought up the magnet to the loop of wire and I saw a momentary voltage. So we're going to talk about that slide, and we'll talk about the other case when I had the magnet close by the loop of wire and then I took it away, and again I saw a momentary induced voltage. So we'll talk about this situation. Both these situations are described by the flux law, by this equation here. So let me say a few words about the flux law. On the left-hand side of the flux law is this epsilon. This is the induced EMF. This is the induced voltage. So first of all, just to get it straight, this is an equation for the induced EMF when you have induction, electromagnetic induction. It's the induced voltage when you have electromagnetic induction. Sometimes we want the induced current. If we wanted to figure out the induced current, we would figure out the induced voltage and then use Ohm's law to find out what current that produces in some wire of some resistance. So it's a law that directly tells us the induced EMF, but it can also immediately, with Ohm's law, tell us the induced current. Those are the 2 effects that happen in induction. You get a voltage spike, you get a current spike. So it's going to tell us that. On the right-hand side, what is this guy here? Looks kind of strange. What that is, so I'll just say it in words. It's the negative rate of change of the magnetic flux. So minus d phi dt is our mathematical coding for the negative rate of change of the magnetic flux. So how does that work? Negative rate of change. So the negative is just this negative sign here. And I'm going to talk about that, not on these couple of slides, but a little bit later, the meaning of the negative sign. So let's focus on, on the right-hand side is the rate of change of the magnetic flux. So how does it describe the rate of change of the magnetic flux? Well, remember our delta is the change of something. Could be the change in the voltage, could be a change in position, so those might be delta V's or delta X's. Here is the change in flux. So this means the change in flux, delta phi, and is divided by the time interval, the change in time that change of flux occurred over. So this is delta phi over delta t is the rate of change of flux. It's the change in flux divided by the time interval. So this is indeed the negative rate of change of magnetic flux on the right-hand side here. And that's what governs the induced EMF, induced current. And that's what governs the size of the induced EMF when calculated using Faraday's flux law. This is his, we sometimes call it Faraday's law, we sometimes call it flux law, we sometimes call it Faraday's flux law, all sorts of things. So let's see if we can apply that law to this situation here. Remember, when we brought the magnet up to the coil, well, we changed the magnetic field, we changed the magnetic flux through the coil. So the coil represents some little surface here, just imagine it, and then we changed the field at that surface, so we changed the flux through that surface, and so let's see if we can figure out the voltage that appears when we move the magnet up to the coil and we change the flux and the field through the surface. This is how we do it. We just do it with this law. So supposing initially that there was zero flux, magnetic flux through the coil. So start out with zero, and then a moment later, half a second later, we've got a flux, a non-zero flux through the coil. Now the fluxes are measured, this is a new unit for us, fluxes are measured in the units of Webers. It's given the symbol WB. So we went from 0 Webers at the starting point when the magnet was far away to 0.02 Webers, half a second later. So we changed the number of Webers of flux, magnetic flux, through the coil from 0 to 0.02, and we did that. It took me half a second to put the magnet from far away to in the coil. So the rate of change of flux, the rate of change of Webers per second, is going to be, well, the change was 0.02 Webers. It took half a second, so I'm going to divide 0.02 Webers by half a second, and that gives me 0.04. That's an induced EMF, that's an induced voltage, the units are volts. And so here's our voltage. And so that's just me using the flux law. If I know how much the flux changed, and I know how long it took to change, I can figure out the rate of change of flux. I can figure out the induced EMF. I did it for the case of pulling the magnet away as well. This also is a case where I'm changing the field through the loop, I'm changing the flux through the loop. If I calculate the rate of change of flux, then that will tell me the induced EMF in the loop. So let's just do the same calculation again. The flux was 0.02 Webers. Then I took the magnet away and the flux went to 0 Webers. So we've got a rate of change of Webers. It took me half a second to change my Webers by 0.02 Webers, and so the rate of change of Webers, the rate of change of flux, is 0.02 Webers divided by half a second. That's 0.04. The units of that is volts. That's the induced EMF. That's the induced voltage that I observe in the coil. And so here is my 0.04 volts. Now, you'll notice in one case, I brought the magnet up, so I increased the Webers through the coil. In the other case, I took the magnet away, so I decreased the Webers in the coil. So the Webers went in opposite directions. We saw by the equation that the induced EMF, the induced voltage, went in opposite directions. In one case it was positive, the other case it was negative volts. The induced current also goes around the circuit in opposite directions. In one case it would go clockwise, the other case it would go counterclockwise. We'll come back to the directions a little bit later. Okay, quiz. Okay, what time are we? We are 10:15. I want to make it 10:14, but okay, should be published. This is a question about induction. This is a question about induced currents, induced voltages. In this question, we've got a uniform magnetic field. We've got a loop of wire that's in that uniform field, and we do various things to that loop of wire. And they're all listed down here. You know, one thing we do is crush the loop of wire. The other thing that we do is we rotate the loop of wire. Another thing that we do is move the wire along the horizontal axis, that horizontal black line in the slide. And then the final thing we did actually, which was not changing the loop of wire, but we turned the field off. So one of those does not change the, does not induce an EMF and does not induce a current. One of those does not involve induction. So the question is, which one doesn't involve induction? Yes. Oh yeah, that's a good question. I'm rotating it about the, see that vertical axis? So I'm spinning it around that axis. Yeah, that's actually a very good point. That's a little bit, I'm not sort of, here's the field coming towards me. I'm not, and here's the loop of wire. I got hold of it like a hula hoop. I'm not turning it like this, like a steering wheel. I'm literally rotating it like this. So that's actually a very important point. Okay, so this is an example of induction, induced currents, induced EMFs. To have induction, you've got to have, through the loop, around the loop, you've got to have a changing magnetic flux through the loop. So, you know, if you turn the magnetic field off, most obviously, right, you'll go from a magnetic flux through the loop to no magnetic flux through the loop. That induces an EMF. If you let's see, crush the loop. If I got hold of that loop, that big hula hoop shaped loop, and I crushed it down to nothing, well, there was a flux going through the loop, but now crushed it, there's none. So that's a change in flux, so that would create an induced EMF. If I rotate the loop about the vertical axis, so it says rotate about this vertical axis here. So I've got the, so that means I'm going to rotate it like this, turn it around. Well, in some geometries, like the geometry on the picture, I've got a lot of field lines going through the loop. But if I turn it 90 degrees like this, I'm holding it like this with the field lines going left to right, there'll be no field lines going through the loop. And then if I turn it round over here, again I get a lot of field lines going through the loop. So rotating the vertical axis, that'll create changes in flux, so that will have an induced EMF. The only one that doesn't create an induced EMF is if I grab that loop, that hula hoop, in this magnetic field that's left to right again, I just walk it like this. I just walk it like this. Always the same number of field lines are passing through the loop. I never change the number of field lines, and so I don't induce any induced EMF, induced current. And so moving horizontally in a uniform magnetic field won't create an induced current, won't create an induced EMF. I want to say a word about the direction, the orientation, the sense of the induced EMF, and the sense of the corresponding induced current. These words I'm going to say are about a law that's called Lenz's law. So there's an interesting, Faraday's law is an interesting law. Within Faraday's law of induction, the minus sign is a law in itself, and it's called Lenz's law. So that minus sign is Lenz's law. Let's see what this is telling us. So when you have induction, that actually involves two distinct magnetic fields. We haven't really talked about that yet, but it involves two distinct magnetic fields. So there's the magnetic field that creates the induction. So that's the field in green here from the bar magnet in this example. So that's the kind of the original magnetic field. It's going to change. It's going to create the induced EMF, induced current. But there is actually, if you think about it, going to be a second magnetic field. It's only going to be a momentary, fleeting, instantaneous magnetic field. But there's going to be a second magnetic field, a momentary magnetic field, when the original magnetic field is changing. That second fleeting momentary magnetic field comes about because when you induce a voltage and you induce a current, that induced current creates a magnetic field. So this induced current in this little loop here will create a magnetic field. And I pictured the orientation of that magnetic field. It's here. This little magenta arrow is the direction of the magnetic field in this situation. And the minus sign in Faraday's law of induction is really a reminder. It's a kind of subtle or not so subtle reminder that there's two fields when you get induction. There's the original field, there's the induced field, the green and the blue fields in this sketch. And the rule for the induced field is it's always opposite the change in the green field. So the green field's going to change, and if the green field changes, we're going to create an induced field which is opposite to that change, opposes that change. So let's see how all that works in this situation. So in this situation, I move the magnet close up to the coil of wire. So I've moved it up to the coil of wires, and I've created a field. I've suddenly created a field, if you're the coil of wire, that is going towards the left. I suddenly see a field towards the left. That means that in the induction process, I'm going to induce a magnetic field due to the induced current that is in the opposite direction. It's going to try and oppose that. So the magenta field is in the opposite direction. That's Lenz's law. If the magnetic field is in the opposite direction, so we've induced a magnetic field from the left to the right, I can use my right-hand rule for a current loop. So this is last class. Right-hand rule for a current loop, knowing the direction of the magnetic field at the center of the loop, which is represented by my thumb in the right-hand rule for a current loop, my fingers curl in the direction of the current that's flowing around the current loop. So that tells me the sense of the induced current. So the steps are, I create a changing magnetic field. That, by bringing up the bar magnet, that was a field towards the right. I understand that that will induce an induced magnetic field that will oppose that, so that induced magnetic field is towards the right. Did I say that the wrong way around? The original one's towards the left, the induced one's towards the right. Once I know that direction of that induced field towards the right, my right-hand rule tells me that the current that flows must be coming out, in this picture here, it's coming out of the screen upstairs, and then it's going back into the screen downstairs. It tells me the sense that the current is flowing around the loop. And so that's Lenz's law. Let me show you the next slide. So this is when I pull the magnet away. So I'm going to pull the magnet away from this loop of wire. So in this case, there was a field towards the left, and now it's gone away. So that's the opposite change of the previous case. Before we had no field, and we created a field towards the left. Now we got a field towards the left, and it's going to go away. How do I oppose that change? The way the induced field opposes that change is it tries to replace it. The green field, the magnet's field, has disappeared. I want to oppose that disappearing field, oppose that change. I'm going to try and recreate it. So in this case, the induced EMF is going to be, the induced magnetic field is going to be towards the left. That's the opposite direction. That means my fingers of my right hand that represent this coil carrying a current inducing a magnetic field are going to curl in the opposite direction. The current's going to flow out at the bottom and upwards and in towards the board at the top. So it's going to curl this way. The current's curling this way. And so again, that's the Lenz's law. That's how we figure out the orientation, the direction of the current that's flowing, the induced current. Here's a second example of Lenz's law. This is with a solenoid and a coil rather than a magnet and a coil. So in this example, nothing's moving. I'm showing you the coil, that's this loop of wire here, and the solenoid. I'm showing you it at one moment in time on the left, a later moment in time in the center, and then a further later moment in time on the right here. So it's just three pictures of the same coil and same solenoid at three different moments in time, walking from the left towards the right. Initially, the solenoid is switched off. So this switch is open. So there's no magnetic field. This picture in the middle is the moment that I switch the coil on, the solenoid on. And I create a magnetic field. And in green, I'm showing that magnetic field. So that's the instant of switching on the solenoid. And then later on, some time goes by, I have a sandwich, and then I switch off the solenoid. And this is the moment I've switched off the solenoid. This is the moment when the magnetic field of the solenoid has disappeared. Over here on the left, while the solenoid's just sitting there on the desk with the switch open, there's no induced current. In the center here, this is the moment I've switched the solenoid on. There's a changing magnetic field. So there is an induced current. And then there's a period, I had the sandwich, that there's no change in the magnetic field. There's no induced current. But when I switch the solenoid off, then at that moment again, that moment when I'm opening the switch, there is again an induced current in this loop here. If we wanted to know the direction of the current in the loop due to the switching on and off of the solenoid, that's another example of Lenz's law. And so I just want to go through this second example of Lenz's law. So let's think about this picture here when we switch on the solenoid. When we switch on the solenoid, we're told that this end of the solenoid is the north pole, this end of the solenoid is the south pole. The field lines are coming out towards the left over here. The field lines are going in at this end towards the left. So we suddenly created a field that's going towards the left. If I suddenly create a field towards the left, and you're a loop of wire, you're going to have an induced current, an induced EMF, that is orientated, that has a direction, that will try and oppose that change in the magnetic field that suddenly appears. So if we create a field towards the left, I'm going to induce a magnetic field that's towards the right. So be induced, that's the magenta arrow in this picture, is going to be in the opposite direction. It's going to be towards the right. That allows me to figure out the sense of the current, the induced current. All I got to do is use my right-hand rule for a current loop. I'm going to point my thumb in the direction of the induced field. It's towards the right. It's opposing the change. My fingers curl in the direction of the electrical current. They're curling such that they would come out of the screen at the top and go back into the screen at the bottom. So the current is coming out of the screen up here and then going back into the screen down here. And that's the right-hand rule applied to this induced magnetic field. Now, then later on, after the sandwich, I'm going to turn off the solenoid. So when I turn off the solenoid, I had a magnetic field that was towards the left. It's going to go away. It vanishes. So what am I going to do in my coil if I want to oppose that change? I'm going to try and replace that magnetic field. I don't like change. You know, people don't like changes, but coils really don't like changes. And so the coil wants to undo that change, replace that change. So there was a field towards the left. It's going to make an induced field towards the left. So again, I can use the right-hand rule to figure out the direction of the current that creates that induced field. The induced field is going to be towards the left. It's going to replace the change. And if I point the right thumb towards the left, my fingers, by the right-hand rule for a current loop, will curl in the direction of the current. They're going to come out of the screen at the bottom and head back in at the top. So this current is flowing out at the bottom and heading back in at the top to create this magnetic field, this induced magnetic field that's opposing the disappearance of this original magnetic field. Everything in this slide about the direction of the induced magnetic fields, the direction of the induced currents, is actually the same as in the previous two slides. Because I really did the same thing. In one case I did it with a bar magnet, making a field towards the left and then taking it away. In this case I did it with a solenoid, making a field towards the left and then taking it away. So all the arguments that led me to the directions of the induced currents, whether they come out of the screen at the top or go into the screen at the bottom or vice versa, they were the same for the two examples, the bar magnet example and the solenoid example, because the changing fields from the solenoid or the bar magnet were the same changes. Okay. Everybody okay with that? That's it, you know, it's a tricky series of arguments I just made there. And I think, you know, there's nothing like working through examples like this on your own and see if you get from the beginning to the end to learn it, right? This is a case where, you know, I could stand up here and give you examples of Lenz's law, and I think you'd all think, well, it sounds right. But it's really, the way to really learn Lenz's law is to take a few examples yourself. So I would encourage you to do that. At least that was helpful for me. Okay, so let's look at some examples of Faraday's law of induction. So, transcranial magnetic simulation. Probably know about it more than I know about it. But it is a way, basically you put your head in a big magnet, they switch that magnet on for a moment, they turn that magnet off, and at those moments that they switch that magnet on and turn it off, right, there's going to be induced currents, induced EMFs. And there's induced currents in your head. in your brain, and those induced currents are used to, I don't know, you're having negative thoughts about something, we can stop you doing that by kicking your neurons with this induced current, induced voltage for a moment. And so this is a real device that's really used. And it's called transcranial magnetic stimulation apparently. Okay, so what are we told? Magnetic stimulation device generates a 1.5 Tesla field. That's a big field. This is slid off to the left. It's in 12 milliseconds, I remember the number, over a radius of a circle inside the brain that's a 1.6 millimeter radius circle. So here it is. So suddenly we created this magnetic field. There was no magnetic field. Then we've got a 1.5 Tesla magnetic field. We've got a changing magnetic field that's 1.5 Tesla. And that changing magnetic field with this device is created over this region, this circular region that has a radius of 1.6 millimeters. And we've got to figure out what is the induced EMF. So this is the induced EMF that's going to affect I don't know how neurons work, but they have these little action potentials, and we're going to make another little potential that's going to change how they're flickering around or whatever they're doing. So what is the induced EMF? This is obviously, I realize, not drawn to scale. Our brains aren't 2 millimeters across, hopefully. I think I'll do this on the document camera. And I started it here, so I made a little sketch for myself, and it has the magnetic field. Those are the field lines that are going towards the right here. It has this loop, this circle, a radius 1.6 millimeters, which is the area in which we're creating this magnetic field, and we want to figure out the induced EMF. I annotated the sketch with some of the things we're told in the problem. We're told the magnetic field change was, so this is really like delta B, was 1.5 Teslas. We're told that change took place in 12 milliseconds. We're told that the area of the brain over which that change took place, well, we're told that the radius was 1.6 millimeters, so it's 1.6 times 10 to the minus 3 meters, but I can change that into the area, which is a more useful thing when working with the flux law. And the area came out to be 8 times 10 to the minus 6 square meters. So we want to figure out the induced EMF. So what's the path through this problem? We want to figure out the induced EMF, which means we need to figure out the rate of change of the magnetic flux, because the rate of change of magnetic flux determines the induced EMF. To figure out the rate of change of magnetic flux, all we've got to do is figure out what the change in flux was, what the time interval was, and divide one by the other. And so the steps for me in solving this problem was, first I'm going to find the change in flux, delta phi. The change in flux is, in this case, is the change in field times the area. It would be the change in field times the area times the sine of the angle between the field and the area, but the sine of the angle between the field and the area, sorry, the cosine of the angle between the field and the area is the cosine of 0 degrees. A and B are perpendicular in this geometry, and so it's just a factor of 1, so I dropped it. Okay, so this is 1.5 Tesla times 8 times 10 to the minus 6 meters squared. That gives me the change in flux. I got it to be it was pretty obvious actually. It's going to be 1.2 times 10 to the minus 5, and these funny units are Webers. So that's the change in flux. Now I want the induced EMF. Well, now I can use the flux law. We're only going to figure out the size of it. We've talked enough I've talked enough about the direction of it. So let's just figure out the size of it. So I'm just going to take the size of the change in flux divided by the time interval over which that occurs. This is Faraday's flux law. And so this is going to be 1.5 times 10 to the minus 5 Webers divided by the time interval that was 12 milliseconds, so it's 0.012 seconds. And if I carry that calculation out, I got, well, look, even that one's easy, gosh. This is 1.2, by the way. I've got a 12 over 12. And so this just comes out to be 1 millivolt, 10 to the minus 3 volts. And so that's the induced voltage in the, around this loop inside our brain. And this induced voltage that's going to kickstart or kickstop those neurons. Okay. That was one example. Let's go back to Lenz's law for another example. In this particular example here, I've got, I'll put this back on. I've got a current carrying wire carrying a current vertically, indicated by that magenta arrow. So that's in the center of the screen. And then I've got 3 loops of wire in the neighborhood of this current carrying wire. So they're in the neighborhood of a current carrying wire, they're in a region of magnetic field that surrounds the wire. And we're going to move these 3 loops. I labeled them A, B, and C. We're just going to move them. And we're going to move them in different directions. So this one upstairs here on the left, I'm going to move it up. This one downstairs here on the left, I'm going to move it towards the left. And this one over here on the right, I'm going to move it towards the right. And the question is, what are the induced currents? What is the orientations of the induced currents, if there are induced currents in each of these loops? And so this is a question about Lenz's law. So the first thing we have to recognize is, what is the magnetic field that these 3 loops are immersed in? It's the magnetic field of a straight wire. There was a right-hand rule for the magnetic field of a straight wire. You point your thumb in the direction of the field of the current, which is up. Your fingers curl in the direction of the magnetic field lines. So the magnetic field lines will come out of the screen on the left-hand side, of the wire, vertical wire, and they will go back into the screen on the right-hand side of the vertical wire. So that's the orientation. So there's a field coming out of the screen over here, it's going into the screen over here. It's strong near the wire. It's weak as you get further from the wire. Okay, so what about this wire here? We're moving this wire vertically upwards. How's the flux through that loop changing? It's actually not changing, because it's always the same distance from the wire. It's always bathed in the same magnetic field. It always has the same flux through it. A has no induced EMF. What about B? What about B? B is being moved away from the wire. So it was in a region of strong magnetic field, so it had a large magnetic flux through it. It's going to move to a region of weak magnetic field, where there's less flux through it. The field lines are coming out of the screen on that side of the wire. Remember the right-hand rule for the wire. So the field's coming out through loop B. So as it goes towards lower field, smaller field, it wants to try and replace that field. The induced field in B will be a field that is also out of the screen if I'm moving it away from the wire. So my thumb is the direction of the induced field in B, and my fingers will curl in the direction of the induced current in B. So it's going to go counterclockwise. The induced current is counterclockwise in B. Well, I'll leave C for you. again, it's in a region of magnetic field. It's being moved in that region of magnetic field. You want to think about the change in the magnetic field to figure out the induced magnetic field and hence the direction of the current. In today's class, just to summarize, we've introduced